So regularization was discussed in the context of linear models in the first week of the course to reduce overfitting. We can also use regularization in deep networks to reduce overfitting. And in particular, it's especially important in deep networks because deep networks can have millions of parameters. So here's a plot of various deep neural networks as a function of the number of operations that they perform and as a function of their performance on ImageNet. And the size of each of the balls, which represents each of these different networks, is proportional to the number of parameters that each of these networks has. And many of these state-of-the-art networks, you can see, have performed thousands of operations and contain over 40 million parameters. So how do we prevent overfitting in these deep networks? You can use L1 and L2 regularization, just like you can in linear models, and we're going to use that in the tutorials today. You can also use a technique called batch normalization, and this helps to keep your activations at a similar size and distribution across layers to improve optimization. It's especially important if you have very deep networks. We can also use a technique called dropout, which randomly removes units from the network during training, but this approach is not used so often anymore. And then finally, you can reduce the number of parameters by using techniques like using convolutions, and that in fact we're using convolutions today in part just for that reason. So how does L2 regularization work? So we have a cost function which is going to be our ordinary squared error loss term plus an additional term which is a penalty on the norm of the weights. And this prevents the weights from being large and potentially just being large to fit some noisy aspects of the training data. So if we differentiate this cost function, we get the first term, which is our usual gradient of the loss function with respect to our weight W, plus a term that's 2 times lambda times the sum of the weights. So for a given weight, the update is going to be subtracting our original loss gradient here, plus subtracting the term that's proportional to the weight itself. And so if the weight is positive, you're going to subtract a positive value and push this weight towards 0. Likewise, if the weight is negative, you're going to be subtracting a negative value, which is addition, so you're going to be pushing that weight up. So whether you're positive or negative, these weights are going to get shrunk to 0. And that's why this type of regularization is called weight decay. And you can implement this in your optimizer using a weight decay as the weight decay parameter as an input, or you can add it to your network manually, which is what we do in this case, where we take the weights of our linear layer and we add this L2 penalty, which is going to be squaring the weights and then summing them. What about L1 regularization? So L1 regularization adds a penalty, which is the sum of the absolute value of the weights. And now this results in an update rule that only depends on the sign of the weight itself. So this is going to be larger than the weight decay penalty usually, and it's only going to be 0 when the weight is set to 0. Otherwise, it's going to be +1 or -1. So this means that L1 produces more sparse solutions, which in the case of the encoding models is useful because it's easier to predict, to interpret these models when they only have a few positive weights, such as they're only adding a few different convolutional filters. However, it can often be harder to optimize these types of functions. So here's a diagram which can help you differentiate between L1 and L2 regularization. So these two axes are the two weights, and H0 is the solution space, which minimizes the original cost. So the H0 solution minimizes the L1 penalty when it intersects with this square here, and it intersects with this square when x1 is positive and x2 is 0. We can look at the same thing for L2 regularization, and where H0 intersects with the minimization of this cost is this circle instead, and this intersection happens where both weights are positive and small. So L1 is producing these more sparse solutions where fewer weights are non-zero, whereas L2 is reducing the size of these weights.